So today we will discuss about the quantization of the Dirac field, and as we remember that Dirac field was something, or Dirac particles were something which we landed up while demanding for relativistically consistent quantum theories. Today we will try to go a quantum field theory version of that, but in this case we have to be slightly careful corresponding to the case when we were doing the scalar field, because scalar field was a trivial case and the scalar field did not transform at all under Lorentz transformation. However, we have given the Dirac particles a name spinor, and here in this discussion it will become what does it mean to be a spinor and what properties a spinors carry and how do they transform under Lorentz transformation. Clearly it is not a scalar, so it is going to transform, but how do these things exactly transform is a discussion which we should do slightly carefully, and then we will move on to, once we are comfortable with knowing the structure of how does it transform, into writing a consistent Lagrangian and obtaining the operators corresponding to that. To recall things, remember we wanted a first order differential equation consistent with the relativistic transformation or special relativity, and we ended up getting this kind of Dirac equation structure, okay, where I have the first derivative of some Dirac particles wave function, and that turned out to be equivalent to the spatial derivatives and the total mass energy content multiplied with coefficients alphas and betas, which turned out to be the case that they can no longer be the number or the usual vectors. They better have to be matrices, 4 cross 4 dimensional matrices. If you recall, the minimum they can start with is a 4 cross 4 dimensional 4 cross 4 dimensional matrices. Therefore, this equations to make sense, this psi appearing here and here was a 4 cross 1 dimensional column vector. So this equation's structure is consistent with spatial relativity at the cost of making this alphas and betas appearing over here into a 4 cross 4 dimensional matrices, and this psi appearing over here as a column vector of 4 objects. This might remind you something very similar to space-time vectors a0, a1, a2, a3, but we will see in a minute that these are though closely related to those quantities but are slightly different compared to the space-time vectors. So these 4 components do not transform as the 4 component of space-time exactly one-to-one. They are slightly related, but they have a somewhat different structure. At more mathematical group theoretical level, they are close by objects. They are isomorphic to each other in some sense, but we will not go into that details. We will just alert you that these quantities transform non-trivially. They neither transform like a genuine space-time vector just directly, or they do not transform as a scalar as well. Okay, and once we will try to find out what is this thing psi1, psi2, psi3, psi4 transform, how does this object transform, we will want to make a quantum field theoretic version, and therefore want to convert all these quantities psi1, psi2, psi3, psi4 into quantum operators. Okay, for that to happen, remember we need to get its phase space, its conjugate momenta, its Hamiltonian, and so on, and therefore we will need a Lagrangian corresponding to that. And Lagrangian, whose equation of motion is this, just like for Klein-Gordon equations of motion, we had written down a Lagrangian which got me the correct differential equation or correct equations of motion. Similarly, I want a Lagrangian for the Dirac particles as well, or Dirac field as well, whose variation will give me this equations of motion. And to no surprise, I would want that Lagrangian to also have the compatibility with special relativity. I should write down a Lagrangian which not only gives me the correct equation of motion under variation, but it respects all the symmetry of special relativity as well. Again, to reiterate, I want to extremize the action. For that to happen, action and therefore the Lagrangian should be a real number functional. That means at the end of the day, once I'm done with all integrations, it should give me a real number, not a matrix, not a complex number. Right now, the equation of motion is a matrix equation. So Lagrangian, what should I write? Should not be a matrix Lagrangian. I should have rather a scalar Lagrangian. Remember, Lagrangians actions are to be real number, real scalar real number based scalar functions, because extremization greater than smaller than is known for us, at least trivially, for real number cases. So therefore I want a Lagrangian which is a real number functional, which also has all the symmetry of special relativity inbuilt in, and from there I should get this equations of motion, and afterwards when I have this complete set, I would try to write down the operators corresponding to the phase space variables. The Poisson bracket will be converted into quantum operators. That is the job which we did for scalar field as well. Here also we are going to do this. The middle aspect of this is going to be slightly problematic, that I have to write down a Lagrangian which gives rise to this equation of motion. Is not difficult, that I can write down. I can just straight away give you, but we will see that writing a special relativity compatible Lagrangian is slightly non-trivial in this case compared to the scalar field case. Let us see why. Okay, so first the Dirac equation which we are going after, this I can bring the whole thing into the left hand side, and therefore the whole quantity can be written like this after a multiplication of the beta completely. So let me reiterate what I've done. I will multiply the whole equation with beta here and beta here and a beta here. This beta times beta will become beta square, and if you remember, beta square was identity. So I will be left with a beta here and beta times alpha over here and an identity over here, and then I will bring the whole left hand side, whole right hand side into the left hand. If I do so, I will have an equation like this at hand: iota h bar beta times the temporal derivative plus iota h bar beta times alpha I, which has come from the left, minus mc times identity is here, so but I am not writing that. That identity was coming from beta square. Okay, so I have this structure. What I am going to do further, I am going to call this is one matrix and these are three matrices: beta alpha 1, beta alpha 2, beta alpha 3. There are three matrices, and this is just a single matrix. So what I'm going to do, the collection of this beta and the three matrices here, as I'm just relabeling them, calling this, the first one as gamma 0, this is a matrix, and the remaining three also as three different matrices: gamma 1, gamma 2, gamma 3. This is just for convention, notation wise convenience we are going to write up. All the time I do not want to write beta times alpha 1, beta times alpha 2, rather gamma 1, gamma 2, gamma 3. Okay, so with this nomenclature, this is nothing physical meaning or any importance of any relevance. I'm just making a convenient writing choice. The equation over here can be written as gamma 0 del psi upon del t plus gamma I coming with the different spatial derivatives. Okay, the convenience is that collectively these derivative terms can be written as a gamma mu del mu psi. Remember, mu and mu are appearing in the diagonal. Einstein convention holds. It will be gamma 0 delta 0 del 0, gamma 1 del 1, gamma 2 del 2, gamma 3 del 3. So all these four terms will be generated. So with this choice, I have a neat convenience at hand that whole this big term can be just written as a gamma mu delta mu or del mu of psi. Okay, and then minus mc psi. So I have written the Dirac equation in a convenient way as this: iota h bar gamma mu del mu psi minus mc psi is equal to 0. Remember again, this is a 4 cross 1 dimensional vector, this is a 4 cross 1 dimensional vector, gamma mu is a 4 cross 4, and there is identity hiding somewhere here which is also 4 cross 4. We previously knew what are the properties of alphas and betas. From there we can derive the properties of gamma mu's as well. The first one would be gamma 0, which is same as beta. So all its properties of beta will be translated into gamma 0. For example, beta square was identity, therefore gamma 0 square will also be identity. What about gamma I, gamma 1 square, gamma 2 square, gamma 3 square? You do the exercise. You take gamma 1, multiply it with the gamma 1. So you will have this structure. And remember, alpha and beta used to anti-commute. If you remember, they had some anti-commutation rule, so you can flip them. Once you flip them, you will bring either alpha i's along it, or if you flip this pair, you will bring alpha in between and beta on the right hand side, Or you do the other way, you flip this version, you will get a beta beta in between and alpha alpha on that side. Either case, you will end up getting either minus alpha I square or minus beta square, which is equal to minus identity. Okay. So the three matrices which we have redefined have this structure. Gamma 0 square is identity. The three gamma 1, gamma 2, gamma 3's individual squares are equal to minus identity. Further, what is gamma I times gamma j? Again, write out gamma I times gamma j. Use the flipping relations once more, that you will flip the middle pair this time with a minus sign. So this beta will come here and you will get a minus beta square. This is an elementary exercise you can do and do with some 2 minutes. You will be able to see that gamma I gamma j is equal to minus gamma j gamma I. That means they anti-commute. That gamma I gamma j is 0 if I and j are different. If I and j are the same, then you will get a minus identity, twice of minus identity. And gamma I gamma 0 lastly, again write down what is gamma I, write down what is gamma 0, flip it once and you will get minus gamma 0 gamma I. Again, they anti-commute with each other. So you have a gamma 0 square which is identity, gamma 1, 2, 3 individual square which is minus identity, and all of them anti-commute with each other. Collectively, I can write down the all set of all these relations which we have written. This one, 3 relations here, 1 relation here, gamma, these relations here, and these relations here. Collectively, they can all be summarized as this equation. Gamma nu anti-commutator is minus twice of eta mu nu identity. Eta mu nu is minus 1 1 1. So you see, all the relations which we obtained can be obtained from various components of this. If I put gamma 0 mu is equal to 0, mu is equal to 0, I will have a 0 0 here. Eta upper 0 0 is minus 1, you will get a twice identity, and therefore gamma, twice of gamma 0 square is twice of identity. That means gamma 0 square is identity, and so on. All other relations can be similarly derived from this. Now, with this, after identifying the properties of hand, I have this matrix equation as the Dirac equation. Iota h bar gamma mu del mu minus mc psi is equal to 0, which is a matrix equation. Our job is to find out how the psi transforms under Lorentz transformations and what happens to this equation under Lorentz transformation. Previously, we had argued that under Lorentz transformation, the equations of motion should remain the same, which we would want in this case as well. So therefore, the Lagrangian should also carry that property. And in order to have a consistent Lagrangian, I should know how different components transform. For instance, for scalar field, I know that it does not transform at all. So either I can say that it transforms with an identity matrix, which is just 1 cross 1 dimensional identity matrix. It does not transform at all. For a vector, on the other hand, we know any vector is given to me, it will transform with a multiplication of this lambda matrix, Lorentz transformation matrix. Remember, that would be a 4 cross 4 dimensional matrices, and this will act upon the 4-dimensional vector and give me a new 4-dimensional vector, A prime mu. So this is how the vectors are supposed to transform. They are supposed to transform with 4 cross 4 dimensional matrices. If I think of a tensor, B mu nu, mu can take value 0 1 2 3, nu can take a value 0 1 2 3. Overall, B can take 16 value 0 0 0 1 0 2 0 3, and similarly up to B 3 0 3 1 3 2 3 3. So there are 16 component object that transforms as two lambdas. Remember, we had defined tensors like how many upper indexes are there, those will transform with those many lambdas. So these matrices, they will transform. This set of this matrices, you can see collectively it can be written as 16 cross 16 dimensional matrices. This is a 16 dimensional object and this is also 16 dimensional object. There are 16 component objects. So together, ultimately it is generating a 16 cross 16 dimensional matrix. Overall, there are 256 objects in this. Alpha can take value 4 value, mu can take 4 value, nu can take 4 value, and beta can take 4 values. Overall, we have 256 such different objects. These constitute components of a 16 cross 16 dimensional matrix, which will act upon a 16 dimensional vector and give you a new 16 dimensional vector at hand. So you see different scalars, different tensors, and so on. Despite the way we have written it, classified, what is happening that they are transforming via some matrix. In this case, a trivial matrix, which is identity. In this case, a 4 cross 4 dimensional matrix. In this case, a 16 cross 16 dimensional matrix. If I take 3 rank tensor, then there will be further objects which will come about. And therefore, this is how the things will keep evolving. So therefore, depending upon their structure, their species, whether it is scalar or a vector or a tensor, a general species transforms via some matrix. Okay, and these matrices are called the representations of Lorentz transformation. Which matrix will transform what object is the story of the representation theory of Lorentz transformation. In this course, we are not going to discuss in elaboration what is the representation theory and what are its something called irreducible representations of Lorentz transformation, Lorentz group. Those are elaborate discussions of some other course, most likely in quantum field theory course, which is available. You can get this. But I will just touch upon the basic structures and guide you towards seeing that the spinors also have this structure, that they are neither of scalar nor the vector nor the tensor, but somewhere in between, that they are also some n cross n dimensional matrices transform them, but not as simple as these. Okay, so we will see in a minute. So the bottom line is that whatever species we think of, a scalar, vector, tensor, spinor, all of them have a common property that under Lorentz transformation, they transform via some matrix. And that matrix is called a representation. This set of matrix is called a representation of a Lorentz transformation. Okay. So we have already named the Dirac equation or Dirac 4-component object as a spinor. We will do a brief discussion to look upon on the spinor representation of the Lorentz group. That means for spinors, what matrices appear that make the spinor vector, a spinor object, not the spinor vector. Vector would be a bad name now. This is a matrix, column matrix, 4 cross 1. That is a spinor. And spinors transform with a matrix which is of the Dirac spinor transforms with a matrix which is 4 cross 4 dimensional matrix. Vectors also transform with 4 cross 4 dimensional matrices, but the spinor and the vectors are not one-to-one in the sense, are not the same thing exactly. They are closely related, as I discussed in the beginning, which we will not touch upon in this discussion. But the statement is that the spinors do not literally transform with this lambda mu nu, because they are not vectors as such. But they are Dirac spinors are something called a bi-spinor, which is closely related to a vector. That's why they have a 4 components just like vectors as well. But they are not just quite the vector as we are familiar with. Therefore, they transform with something different, not with lambda directly. Okay, and what do they transform with? That we will see in this discussion. Okay, so just to do a quick survey, what is a representation, and then I will give you the essential features, what is there for the Lorentz transformation and what is their representation. Remember, we are going to look for a representation of a Lorentz group. Before that, we should just be clear about what do we mean by a representation. So representation is basically writing the action of Lorentz transformation through an action of matrix on some vector. For example, here this was a 4 cross 4 dimensional matrix which was acting upon a 4 cross 1 dimensional vector. Here it was 16 cross 16 dimensional matrix which was acting upon 16 cross 1 dimensional vector. So ultimately, a representation is identifying certain matrix acting upon certain vector, which is essentially capturing the features of Lorentz transformation. Then the question will arise, what matrix will do that and what vector it should act upon? So the basic statement is that any n cross n dimensional matrix and any n cross 1 dimensional vector which respects the essential features of the Lorentz group. This is a cliched statement now, the essential feature or the soul of the group. What is the most important thing about the group through which it is identified is called the Lie algebra. This is again a terminology. You should not be too much of worried about that. What it is, we will just see what does it mean to be some group. So this is some identification feature of a group should be identified, that this is how you identify a group. Since a group, as we are talking about representation, I am not demanding about its dimension to be fixed. I am going to look for any dimensional matrix. So that does not mean that a group will be identified with a size of a matrix. Size of a matrix is a changing thing. In different representation, the size of matrix will change. But still, there should be some essential feature which remains the same across all other different dimensional matrices. And that we have seen already. We will just see in case of simple rotations. We will first see how to identify rotations group and what is the soul of the rotation group. That soul is typically called in linguistics of mathematics the Lie algebra of a group. Any continuous group is identified by the relations between its generators, and that relation is called the Lie algebra. If I change my dimension of the matrix, the size of the matrix will change, the component of the matrices will change, but what will not change is the relation between the generators of that group in any dimensional matrices. We will see an example to make things clear. For example, we have seen in quantum mechanics that rotations are generated by angular momentum. Okay, just like translations are generated by spatial momentum. And we know in Hilbert space how to write down the angular momentum operator. Angular momentum operator is the cross product between the position and the momentum, r cross p, which I have written in terms of epsilon ijk. I hope you are familiar with Levi-Civita tensor, which is a totally anti-symmetric tensor, which 0, 1, 2, 3 is 1 and their cyclic permutations is 1, and any single permutation epsilon 1, 2, 3 is 1. But if you just flip one pair, epsilon 2, 1, 3, 1 and 2 have been flipped, then it will pick up a minus sign. If you maintain the cyclicity, that means epsilon 1, 2, 3 becomes 3, 1, 2. That means I have just given it a rotation. It will maintain the order, then it will be 1. Otherwise, the cyclicity is broken. You have flipped one pair, then it will pick up a minus sign. And for any repeated object, 1, 1, 2 or 1, 2, 2, all those things are 0. So this is a completely anti-symmetric Levi-Civita tensor, which is a convenient way of writing a cross product. Two vectors cross product can always be written as x cross y vectors can be written as epsilon. Let us say I'm talking about ith component of this. The resultant cross product would be ith component of that. That will be epsilon ijk xj yk and sum over j and k. This is how cross product is written for any vectors. So that is what I'm making use of on writing the angular momentum operator in quantum mechanics as cross product between x and p. This is an angular momentum operator in Hilbert space of wave functions. Okay, this generates rotation. This was a rotation in Hilbert space. In position space, what generates rotation? The rotation matrices, if you remember, was cos theta sin theta 0, minus sin theta cos theta 0, 0, 0, 1. This is the rotation about the z direction, z axis, z axis. Similarly, there can be y axis, x axis. There are 3 rotations possible, and generators of this will be infinitesimal form of these rotations. So rotation matrix you take its derivative with respect to theta and put theta is equal to 0 after derivative. That will identify for you what is the generator of that group. There is a iota and h bar multiplication which typically is done in order to make it quantum mechanical operator and such that the rotations and other things are written as quantum operator. But you can simply do that iota h bar multiplication times this is the generator of a group. So take rotation about x-axis, do this operation, you will get this. Take rotation about y-axis, you will get this. Take rotation about z-axis, you will get this. And these are the generators, therefore, of the position space rotation. This was in Hilbert space rotation, this angular momentum, and this is in position space. Similarly, in spin space, you might have done already. Pauli matrices are supposed to generate rotations in spin space. J1, J2, J3. The three components of J1, J2, J3 from here, the three component J1, J2, J3 here, and the three component J1, J2, J3. All of them are angular momentum operators. They are all talking about rotation group. You see, their structure is different. Sometimes it is 3-dimensional, 3 cross 3-dimensional matrix. Sometimes it is 2 cross 2-dimensional matrix. Sometimes it is some linear operators on wave functions. But they are all talking about the same group. So what is common across this? Not the matrix dimension, that is not a common feature. Not the matrix component, that is also not a common feature. What is a common feature such that these operators here, these matrices here, and these matrices here can be claimed that they are all from the same group is the statement that the three component of this, the three component of this, and the three component of this, they all satisfy the same relation, which is given over here, the box. You take J1, J2, find out its commutator, you will get that it is equal to J3 with iota h bar as we have discussed. So that means despite their appearance, their matrix, their size and matrix component, they look very different from each other. But at their heart, they are satisfying the same relation amongst each other, which any rotation group generator would do. So they are different matrices of different size. So this is called spin half dimensional representation. This is called spin 1-dimensional representation. This is spin 0 representation in some sense, because it is not about any spinor object. This is orbital angular momentum. So in general, I am talking about 2j plus 1 cross 2j plus 1 cross dimensional matrices. This will be therefore 3 cross 3. This will be spin 1 will be 3 cross 3, spin 2, spin half will be 2 cross 2, and so on. Their sizes will change, their matrix dimension will change, their components will change. But what will not change is this relation. This will always remain true. And the second relation, that in any space, this rotation is generated by these matrices through this exponential operation. Take the J operator, dot it with the theta 1, theta 2, theta 3, the three directions, how much angle you want to rotate by along this axis, that axis, and that y-axis and z-axis. These two relations will be always true across any dimension or any representation. So I will not care about what is the matrix size, dimension. I will not care about what is the component. I will care whether they satisfy this equation and whether they satisfy this equation or not. If they do, I will call that all of them are rotation belonging to the rotation group. Just their representations are looking different. Okay. So group is an abstract object. In different spaces, it manifests itself as a different matrices. But at their heart, the generators always satisfy this relation. You can verify that here we have written the three things, here we have written the three things, here we have written the three things. Despite their shape and form being very different, they satisfy the same relation. So this is called the Lie algebra of a rotation group. First, we identified how many generators are there. 3 generators corresponding to 3 choices I can make, 3 rotations I could have done. Then I take the rotation matrix, do this derivative with respect to the parameter of rotation, and go for infinitesimal. That means theta tending to 0. Once I do that, I will end up getting the generators of that group, and then I will uncover what is the relation between the generators. You will realize that this relation is always working for any representation of that particular group. So just like rotation is identified with the fundamental algebra of generators it has, we can expect, since Lorentz group is also a continuous group, it should also have some similarly identified or identification algebra amongst its generators. How many generators are there for the Lorentz group? Remember, Lorentz group is a group of spatial rotations and boosts. So 3 spatial rotations are possible along x-axis, y-axis, z-axis, and 3 boosts are there along x-axis, y-axis, z-axis. So three rotations and 3 boosts together are the total operations Lorentz group can do. So there could be 6 generators. Again, I will do the same thing. Lambda is this time is the matrix which will be identify the operations. A simple rotation operation, for example, will be temporal axis is unchanged. Suppose I'm doing a rotation along the z-axis, then the z-axis will also be unchanged. And I will have just cos theta, sin theta 0, minus sin theta, cos theta 0. This will be a rotation operator in the space-time along the z-axis. Again, do the same thing. Do this del upon del theta, put theta is equal to 0. You will generate the 3 rotation generators. Okay, these are given the name J. I have just pulled out a iota. Iota is supplied into the definition of the rotation operator. So I'm just pulling out or absorbed in the definition of theta, let us say. Then the 3 rotation generators are given like this. Okay. Now, similarly, there could be 3 boosts. Boosts, remember, is cos hyperbolic beta, sin hyperbolic beta, then 0, 0, sin hyperbolic beta, cos hyperbolic beta, 0, 0, and then 0, 0, 1, 0, 0, 0, 0, 1. This will be first 2 cross 2 dimensional block is the boost block. Then do the same operation. Take del upon del beta, put beta is equal to 0. That will give you the generator of the boost along the x-axis, and you will find out that you will get this operator, this matrix. So 3 boosts generator are this. 3 rotation generators are this, obtained from del lambda upon del theta I. Theta I meaning along x-axis what direction, y-axis what direction, z-axis what direction, and not is equal to 0. Then first you do this and put theta I is equal to 0. Similarly, for the boost matrix along different components along x direction, y direction, z direction, you can do the 3 boosts, do this operation, you will get these 3 matrices. So these 3 rotation generators and these 3 boosts generators are there. Previously, I had these 3 rotation generators in position space. Their analog are this 6 generator in space-time space. It is not only a position space but time position space. So 6 generators are there. Previously, rotations were satisfying, the generators of rotations were satisfying this algebra, which it should keep doing even in the 4-dimensional case. So this is a rotation subgroup. But there is a boost as well. So boost and boost commutator, if I find out, you will find out that they become, the 2 of them will become third of the J, meaning 2 boosts combined can be written in terms of rotation about one axis, and so on. 1 boost and 1 rotation equal is also commutes to 1 boost. So we had previously 3 generators for rotation, and the 3 rotations were satisfying this relation amongst each other. For Lorentz transformation, we have 3 boosts and 3 rotations, and their Lie algebra is this, the whole block, the bigger block over here. And just like any representation or any matrix in whatever space was obtainable from their generators times the parameter of the transformation, here also we have 6 parameters, theta 1, theta 2, theta 3, beta 1, beta 2, beta 3, and their generators put together give you the representation of that. So what we will have to do, we will have to find out any n cross n dimensional matrices, 6 of them, which satisfy this relation. One simple realization we have at hand. In space-time, this 6 matrices already do that. But we can explore more. We can ask whether in 4 cross 4 dimensional matrices space also, are these the only choices, or there are more choices than that? Similarly, are there choices in not 4 cross 4 dimensional space, let us say 2 cross 2 dimensional space or 6 cross 6 dimensional space, which maintain this relation? So this is the soul of the Lorentz group SO31 group. Just like this was the soul of the rotation group. And then the various representation which we had written over here, they all have the common feature that irrespective of their shape and size, they were satisfying this relation. And the game here is also that irrespective of the dimension and the size, we would have to find 6 matrices which satisfy this relation, and that will generate me representations of Lorentz group. This is the simply given summary of this. One more thing what you can do is that from the generation of from the set of these 3 rotations and 3 boosts what we have, J and Y, which we have over here, we can construct some more things which are equivalent in description but more easy to visualize things with. So if we have 3 J's and 3 Y's, what we can do, we can combine them in a particular manner. That means I can define J plus 3J plus J plus 1, J plus 2, J plus 3, which is nothing but half of J1 plus Y1. Actually, there should have been a iota, I believe, iota here. Yes. So I will define a J plus, which is summation of J and Y with iota in between, and J minus, which is also half Ji minus iota Yi. So I can define 3 components object J plus and 3 component object J minus from this 6 component object J and Y put together. This is just a linear combination of J and Y. The crucial thing about this J plus and J minus is that this J plus talks to only J plus. It commutes to J minus. J plus and J minus commutation is 0. Amongst itself, J plus I and J plus J just commute to the same way as the rotations we are doing. J plus I, J plus J is equivalent to iota epsilon I J K and J plus of K. Similarly, J minus also does the same thing amongst each other, that J minus of I and J minus of J is equivalent to iota times epsilon I J K, J minus of K. So J plus and J minus decouple into 2 independent SO3 groups, 2 independent rotation groups. So the statement is whatever was the Lorentz group, SO31, can also be identified as a 2 disjoint rotation groups. Their 6 generator operators, 6 generation matrices are equivalent to double copy of 2 rotation groups. Okay, and individually each rotation group has its simple rotation algebra. So that means that I can obtain the representation of SO31 group from the 2 copies of representations of SO3 group, the rotation group, which we have already done. The rotation group's representation we already know. For example, this is a rotation group in spin 1 object. This is a rotation group for a spin half object. So I can take 2 copies of this and generate a SO31, the representation of a SO31 or representation of a Lorentz group for spinor objects. Okay, that means I have now in general, so I would have a 2J plus 1 dimensional representation, meaning here I will have a 2J cross plus 1 cross 2J plus 1 dimensional matrix and times another 2J plus 1 cross 2J plus 1 times 2J plus 1 dimensional matrix. Since Lorentz group is a double copy of 2 rotation groups, so therefore its matrix structure will be just direct product of a rotation matrix times another rotation matrix put together. So ultimately I would have this 2J plus 1 cross 2J plus 2J primed plus 1 dimensional representation. I can take any J value, I can take any J primed value. J was one representation, spin J representation, and J primed is another representation of the rotation group. For instance, I can have most simple representation where J and J prime both are 0. Okay, so that means I should have written 1 cross 1 dimensional matrix. So it is a 1 cross 1 dimensional representation. 2j plus 1, j is 0, both j and j primes are zeros, then it is 1 cross 1 dimensional representation, which is just a simple one dimensional identity matrix cross one dimensional identity matrix. Similarly, one possibility of one representation of SO3 group is that the j here takes value spin half and the j prime takes value spin 0. So j is half, j prime is 0. Then this is called a spinor representation, half comma 0. First j is half and second j prime is 0. And its representation is this is the matrix which generates Lorentz transformation on spin half comma 0 object. This is called a Weil spinor effectively. Okay. And similarly, there can be a representation which is reversed way, that first j is 0, the second way j prime is half. Here again it is called d0. Previously it was called a representation of half comma 0. Remember, this is j. These representations are identified by two Lorentz group. One Lorentz group will representation can be j identified with number j. Another rotation group's representation can be identified with j prime. There is no reason for j and j prime to be the same. They can take their independent values. So we are listing out possibilities. First possibility was 0, 0. The next possibility was half 0 or 0 half. The next possibility will be half half, and so on and so forth. So we are just listing down the possibilities and just writing down the corresponding representation matrix. So in half 0 representation, this is a Lorentz transformation matrix. Sigma are the polymatrices, theta I are the 3 rotations, and beta I are the 3 boosts parameters. Similarly, for 0 half representation, these are the transformation matrix. This is how a spinor object of 0 half rank will transform. Remember, Dirac particle was a 4-dimensional thing where the two blocks independently were the spin half. So therefore it is a spin half times spin half representation. J and J prime are both half. That means this transforms like this representation matrix. Take this object, tensor it with this object. That means D half 0 cross D 0 half. That will define how the Dirac particle or Dirac field will transform. See, this is the transformation matrix for a Dirac 4 cross 1 column vector. It is different from the usual lambda mu nu. This is also 4 cross 4 dimensional matrix because this is half half. So half half will mean here 2 cross 2, meaning 4 cross 2 cross 2 meaning 4 cross 4 dimensional matrix. Okay, but it is not lambda mu nu. So this is how the Dirac particles are supposed to transform. Since these are spinors, the spinors are just the half integer representation of the Lorentz group, and the half integer Lorentz group can be identified as a double copy of half integer rotation groups, and therefore this is how the Lorentz transformation will act upon a Dirac spinor. It has a 2 block of spin half spinors. Its Lorentz transformation will be 2 blocks of spin half representation of the rotation group. Okay, so this we have to keep in mind. We can write down, for example, what is this. For example, you know what is D half 0, which is this matrix, exponential I theta I beta I sigma I. You can play around and write down for, let us say, rotation about x-axis and no boost. That means theta 1 will be 1 or parameter theta, all other thetas will be 0. And no boost means all the beta i's are 0. For that, expand this exponential and find out what is the transformation matrix. Similarly, for a boost, you can find out what is the transformation matrix. And from this information, you can also find out what is the representation matrix for the Dirac particle. Okay, so here and here you have to put it the same copy of the d lambda half 0 and d lambda 0 half. There is a relative sign difference between half 0 and 0 half representation in their operators. So all these things go with a detailed discussion which is called chirality of the field and whatnot. We are not going to look at those details because we are not doing field theoretic. More our focus on this course is not about learning more subtle features of the fields. We will just want to develop interaction of quantum systems which we come across in labs to quantum fields. So therefore the useful information we are going to maintain only. The useful information for this discussion is that the Dirac particles, the wave function or the field which is going to be, does not transform very trivially under Lorentz transformation. It transforms with some matrix, and that matrix has to be obtained from this and that put together in the diagonal block of a 4x4 dimensional matrices. Okay, so this is how the psi transforms. Psi goes to the 4x1 dimensional matrix goes to d lambda times 4x1, where d lambda is this, and we have this equations of motion to obtain. Okay, so one thing which we have realized in this discussion is how the Dirac field itself will transform under Lorentz transformation. Then second thing which we wanted to know was to write down a consistent Lagrangian which will give me this equations of motion. Again, if I have this equation of motion, you can find out that the Lagrangian, which I'm again proposing like I did for Klein-Gordon equation, the Lagrangian given over here correctly gives you this equation of motion if I do the variation with respect to psi dagger, not psi bar, psi dagger. If I do the variation with respect to psi dagger, I will get the Dirac equation. If I do the variation with respect to psi, I will get the complex conjugate or the Hermitian conjugate of this equation, the Dirac equation. So this Lagrangian is a good candidate, just like there was a candidate Lagrangian for Klein-Gordon equation. This Lagrangian is a good candidate for starting our discussion on quantization of field. I can use this Lagrangian, find out the momenta corresponding to psi and psi dagger. Remember, psi is a complex field. It has real parts as well as imaginary part. Either you can work in terms of two fields, real components of psi and imaginary components of psi, or you can take psi and psi dagger pair, which is equivalent. So ultimately, any psi is four-dimensional object, but I can write its real part times psi real 1, psi real 2, psi real 3, psi real 4, and imaginary part psi real imaginary 1, psi imaginary 2, psi imaginary 3, psi imaginary 4. So I will have 8 objects, 4 components of the real part and 4 components of the imaginary part, which I have to work with, which is equivalent to having either real and imaginary pair of 4x1 dimensional vectors or psi and psi dagger, which can be identified as linear independent 4x1 dimensional vectors. So I have a candidate Lagrangian which correctly generates for me the Dirac equation, and I can use it to generate the phase space, Hamiltonian and whatnot quantization, whatever we had done. However, one thing which should trouble us at this stage is this is fine that this is a C number as well, because we wanted a real number kind of thing. Real number in the sense of this is psi, this is a 4x1 dimensional matrix, this is also some other 1x4 dimensional matrix here, and in between I have a 4x4. So ultimately they will combine together to give me a matrix of 1x1 or a number which I will get. So our first demand is met that the Lagrangian should not be a matrix, it should give me a real number functional. This looks like happening, that whatever we have written. However, this simple choice which we have written, which does generate the equation of motion for the Dirac particle, unfortunately turns out that it is not Lorentz invariant. This Lagrangian is not Lorentz invariant. How do I see that? The realization is that the transformation of psi, we have seen that the psi transforms with some matrix d lambda, which is half cross half, d lambda half 0, d lambda 0 half. tensor product. This is the overall d lambda half which with the psi transform. That means its dagger will transform with d dagger of this. So psi transforms as d of psi, d lambda of psi. This is a matrix. Psi dagger will transform to psi dagger times d dagger of lambda. That means the terms which are appearing like psi dagger psi here or psi dagger of del mu psi, those will transform with as this. D psi dagger psi will become psi dagger d dagger d psi. So this has psi has transformed to d psi, psi dagger has transformed to psi dagger d dagger. We have in between a d dagger d multiplication. And unfortunately, d dagger d in this case, whatever we have obtained over here is not identity. These are not unitary matrices, which we can quickly see. For example, even if the vector representation we take, the 4 cross 1 dimensional vector representation, there you can see that this is the rotation matrix, one about z-axis, this is about y-axis, this is about x-axis. These are the 3 rotations which are possible. The 3 rotations are indeed generated by unitary matrices. You can take that the 3 rotation lambda dagger lambda is identity. They are orthogonal and therefore it's just a special case of a unitary matrix. However, the 3 boosts which are possible, you can verify that they are not orthogonal or unitary. So even for the vector representation which we have seen, the transformation matrix is not unitary. So you can expect even for spinor representation, it is not going to be unitary always. So therefore it is not a unitary d lambda is not a unitary, and therefore psi, the wave function psi, does not transform in a unitary way under Lorentz transformation. In Schrodinger evolution, which we have seen, unitary transformations, if something evolves with unitary transformation, then most of the physical quantities do not change. But if I write down the Lagrangian like this, which is just psi dagger and psi multiplication, or psi dagger and del mu psi multiplication, these things will not remain invariant under Lorentz transformation. Okay, so with this realization, we stop over here. In the next class, we will see how to fix this once we have identified how the Dirac particles transform.